Dr. P here. This video I'm going to give an example problem of calculating torque and equilibrium. The problem is a man who leaned their ladder against the wall, or a person who leaned the ladder against the wall, walks up the ladder, and the question is how far up the ladder can he get before the ladder slides down. So for this problem, there's going to be some friction with the floor. We'll call that coefficient of friction mu sub s. Let's say that there's no friction against the wall though. Okay, so here's our picture. Let's just do this in general terms. So the ladder, let's have the ladder be mass capital M. We'll have the person, we'll have their mass be lowercase m. Let's call the length of the ladder L. And let's just call that coefficient of friction, of static friction, mu sub s. Okay, so the first thing I'm going to do is draw a picture, which I have. So I'm going to write down my steps to solve a problem over here. So 1, draw a picture. All right, step 2 to solve a problem, that step 2 is going to be to draw your free body diagram. In this case, I'm going to draw my free body diagram right on top of the picture. So I have my force of gravity acting on the ladder, which acts at the center of mass. So this is, we'll call this FL, force of the ladder. And we have the force of gravity from the man or the person. We'll call this FM, acting at the person. Okay, now we get that normal force of the ladder against the wall. I'm just going to call that the force of the wall. And I have the force of friction pushing inward, going inward from the floor, because that force is preventing this ladder from flying out. So this is our force of friction. And we missed one more force, which is the normal force. And that's going to be a pretty big force if we think about summing our forces in the y direction. That normal force is going to be equal to the force of the ladder plus the force of the man. So maybe I'm going to go ahead and step 3, choose my axis of rotation. That axis of rotation that I choose, I'm going to pick it to be in a place that 1, helps me find what I want to know, and 2, makes the most torques disappear, because then it's going to be a lot easier, or it gives me less work to do. So while it might seem kind of counterintuitive, I am going to pick my axis of rotation to be this point where the ladder meets the floor. A little bit of a weird choice, especially because we know that the force of friction is going to matter. But if I take my step 4, and step 4 and 5 are sort of interchangeable, sum the torques, sum the forces. So I might skip step 4 and go straight to step 5 in this case. So I'm going to sum my forces. At this point, I'm going to think, okay, well, this ladder is not accelerating, it's not rotating, and so the sum of the forces in both the x and y directions will be equal to 0. So the sum of the force in the x direction is 0. That means the force of the wall equals the force of friction. So I can still use my force of friction, because now that's equal to the force of the wall. So this pick of my axis of rotation being down at the bottom isn't going to cause me to have any extra unknowns. I sum my forces in the y direction, and that gives me my normal force minus the force of gravity from the person minus the force of gravity from the ladder. I'm going to go ahead and just move this to the other side and do some negatives. So I get my normal force is equal to the force of gravity of the man. So I'm just going to call that the mass of the man times gravity, plus the force of gravity of the ladder, which is the mass of the ladder times gravity. Or we could simplify this and say G times little m plus big M. That's our normal force. Okay. So I'm maybe not quite done with the force of the wall yet. I think the force of the wall equals the force of friction. Force of friction is mu sub s times that normal force. So now this equation only holds true when I'm at the maximum force of static friction. Remember, if I am below that, then it's a less than or equal to value. So I'm at my maximum force of static friction, so I can use this equal to equation. I get mu sub s times g times little m plus big M, the mass of the man plus the mass of the from the ladder. Okay, so this is not giving me how far up the ladder can the person travel. This is really just giving me some forces that I maybe didn't know before. So how far up the ladder can that person travel? I'm really looking for this distance x. If the length of the ladder is L, then this force of the ladder, the force of gravity of the ladder, the lever arm for that acts as L over R, or L over 2, I mean, the distance over 2. And this force acts at a distance of L. Okay, so now I'm going to sum my torques. The sum of the torques is equal to 0 because I'm in equilibrium. And the first torque that is causing a force is this torque due to the man. Now that torque is going to cause a counterclockwise rotation, so that torque will actually be negative. And then the ladder is also in the same direction, causing this to rotate clockwise. So you get that clockwise rotation, and then you get plus the force of the wall, or the torque due to the wall. All right. From here, it's just now some geometry for us to figure out those perpendicular forces. How big are the perpendicular forces compared to our angle theta? If this angle is theta here, then I could drop in a perpendicular line here. And that means this angle will be theta. This is the same idea that we get when we have a box on a ramp, that this is the angle between the perpendicular to the ramp. It's not a ramp, but the perpendicular and the force is going to be theta. So then this angle, this component here is force perpendicular. I can do the same for this guy, so that this force is perpendicular, and this is my angle theta. And then I can do over here, I see that I have two parallel lines, and I have alternate interior angles with this angle theta up here and my theta down here at the bottom. Okay, so with that, my perpendicular force is going to be there. All right, so sum of the torques equals the force, we'll just go straight into negative the force of the man. That perpendicular force of the man, this is my adjacent side, so that's going to be cosine theta. And we'll multiply that by that distance x, minus the force of the ladder, force of gravity from the ladder, times the cosine of theta, times L over 2, plus the force from the wall times the sine of theta, because this is my opposite side now. The sine of theta times L. I'm going to scroll up. From here, it is just math and plugging in the things that we know and the things that we're looking for. So I get negative mg x cosine theta, just moving that x to the front, minus big mg L over 2 cosine theta, plus the force of the wall, which I'm going to go ahead and plug back in my force of the wall from up here. So that is mu sub s g little m plus big M L sine theta. I'm going to move this term to the other side because that's what we're looking for. So I get mgx cosine theta equals negative big M mass of the ladder g L over 2 cosine theta, plus mu sub s g mass of the person mass of the ladder times the length of the ladder times the sine of theta. Divide everything across, divide mg cosine theta across. With a little bit of math and pulling some things out, we will see that we get x equals mu sub s, big M plus little m, times L sine theta over m cosine theta. Minus m over m L over 2. You can turn this sine over cosine into a tangent if you want. And that's it.